Recently, the moment-generating function packaged every moment of a random variable into one function. This video puts those moments to work. When a probability cannot be computed exactly, a single moment can still fence it in. First, the engine behind every bound in this chapter. A function that dominates another has the larger expectation. Then the Markov inequality, which turns one mean into a tail bound, the Chebyshev inequality, a template that mints a whole family of bounds, and the Cantelli inequality, where we choose the best bound from an entire family. Here is a common predicament. We need a tail probability, the chance that some quantity exceeds a threshold and the exact value is out of reach. The distribution is unknown, or the integral is intractable. But suppose we do know one number, the mean. Remarkably, that one number can fence in the probability, and the engine is a simple picture. Take two non-negative functions, g below and h above, so that g of x is at most h of x for every x. Now weight both by the density of x. The density is non-negative, so at every point the weighted g still sits under the weighted h, and integrating preserves the order. The expectation of g of x is at most the expectation of h of x. Pointwise domination survives the integral. One more ingredient remembered from earlier chapters. A probability is itself an expectation. The probability that x lands in a set S is the expectation of the indicator of S, the function that is 1 on S and 0 elsewhere. The strategy is now visible. To bound a probability, sit a computable function on top of an indicator step and take expectations of both sides. Run the strategy on the right tail. X is non-negative, A is positive, and the target is the probability that X is at least A. Draw the indicator of the interval from A to infinity, 0 at first, then a step up to 1 at A. Now lay the straight line x over A on top of it. Below A, the line is non-negative while the step is 0. At A, the line reaches exactly 1. Beyond A, it keeps climbing while the step stays flat. Everywhere on the non-negative axis, the line dominates the step. Take expectations of both sides. The expectation of the step is the tail probability itself. The expectation of the line is the mean of x divided by A. That is the Markov inequality. For a non-negative random variable, the probability that x is at least A is at most the expectation of x over A, one mean, one tail bound. Put a number on it. A queue holds 10 customers on average. The chance of finding 50 or more is at most 10 over 50, 1/5, no matter how the queue length is distributed. The gap between the line and the step is the price of that generality. The bound is often loose, and everything that follows works to close the gap. Nothing in that argument was special about the line. Any dominating function works, and that observation is worth a theorem. Let h be any non-negative function and s any set of interest, and write I sub s for the infimum of h over s, the lowest h ever gets on that set. Then I sub s times the indicator of s sits under h times the indicator, which sits under h itself at every point. Take expectations, and the Chebyshev inequality appears. I sub s times the probability that x is in S is at most the expectation of h of x. When the infimum is positive, divide through, and the template mints a bound for every choice of h in S. The most famous instance takes h of x equal to x squared, and S the set where x squared is at least b squared. The infimum is b squared, so the probability that the magnitude of x is at least b is at most the second moment over b squared. Apply that to the centered variable, x minus its mean, and the second moment becomes the variance. The probability that x strays from its mean by b or more is at most the variance over b squared. This is the form everyone calls Chebyshev, and it is what variance is for. Hold on to it. Run this bound on an empirical average, and out comes the law of large numbers. Coming soon. One worked bound to finish and a preview of a powerful move. Suppose we know the mean m and the variance sigma squared, and we want a one-sided tail, the probability that x exceeds its mean by at least a. Center the variable y equals x minus m, has mean 0 and the same variance. Now dominate with a whole family of parabolas. H of y equals y plus b squared, one function for every positive b. Over the set where y is at least a, the infimum is a plus b squared, and the expectation of y plus b squared is sigma squared plus b squared. Chebyshev hands us a bound for every b. A family of bounds means a choice. Take the best one. Slide B along the curve of bounds, it dips, bottoms out, and rises again. Calculus finds the minimum at B equal to sigma squared over A. Substitute back, and the algebra collapses to the Cantelli inequality. The one-sided tail is at most sigma squared over a squared plus sigma squared. Remember the move. Dominate with a family, then optimize over it. Next video, the family is exponential. The pocket tool is the moment-generating function, and the result is the Chernoff bound. The key idea of this video: probabilities are expectations of indicators. So, dominating an indicator turns one moment into a tail bound.